present this work. Okay, so I want to tell you about what I think is a fairly cool result, but there's also a lot of words and titles, so I need to have a little bit of a discussion first, maybe, about what some of them mean. I mean, I guess I could check you're all like experts in semi-algebraic geometry, then we can skip the first part. Okay, right, so I will try. But yes, all right, so I start with some recollection, but what I should warn you is that I am not an expert in semi-algebraic geometry, so I will communicate to you what I know about the things that are relevant for what I want to do. But what I say might be misleading or perhaps even wrong, not to the best of my knowledge, of course. And so if you think so, please let me know. Very much appreciated. Okay, so also I'm not really going to be doing directly semi-algebraic geometry. I'm going to use the proxy of something called the real étale topology. So I want to recall what that is. Okay, so the real étale topology is a Grothendieck topology of the category of schemes. And it's constructed using the following gadget. So let's say X is a scheme. And then out of this, you can build a topological space. For now, I'm going to give you a set, and I'm going to say a word about the topology very soon. So this is somehow the realification or the real space of X. Okay, so as a set, this realification, I'm just going to write Rx, is the following thing. It's the set of pairs of, let's say, X comma alpha, where X is a point in your scheme, in the usual sense. And so alpha is going to be an ordering of the residue field at that point. Okay, so if you give me some random point and some random scheme, then the residue field, it may have one ordering, it may have many orderings, it may have no ordering, right? So for example, any positive characteristic field is not orderable, or the complex numbers is not orderable. Everyone can prove it's orderable if and only if -1 is not a sum of squares. And then, okay, so it can be difficult to find what they are, but that's the definition. And let me just sort of remind you that an ordering of a field what does that mean? Well, as a data which you have to give me is, let's say, the set of non-negative elements. Okay, so it's, let's say, the set K greater than or equal to 0 contained in K. And of course, then you will have to have some axioms, which I'm not going to write out. So, for example, every square should be non-negative. That's one of the typical axioms. And the sums of non-negative things are non-negative. The products of non-negative things are non-negative. Maybe that's all axioms or not, I don't remember right now. But they're using okay, and now using this real, well, for now just the set, but the real space of X, you can define the real étale topology as follows. So we call a family of maps, maybe I'm going to write the family of all maps. Something like this, I don't know, Fi, Xi to X, and each of these is an étale map of schemes, and you want to say when is this somehow a covering in our new topology, or it's not my topology, as we studied for a good while. So we call this a real étale covering. Call this family, yeah, a real étale covering. And also, like, writing real étale all the time is getting pretty quick, so I'm often going to abbreviate this to somehow ret. Like, étale is often abbreviated to et, and then you put an R in front. So clever people come up with these things. Not me again. Right, okay, if, well, as all of these maps are étale, as I said, and you're going to guess, like, I mean, the realification of X should be the union of the images of the realification. So it's clear that any map of schemes gives you a map of realifications, right? Because you get a map of the residue fields in the other direction, and there's an embedding, so you can restrict the ordering and so on and so forth. So it is a real étale covering if Rx is equal to the union of of these. So that's just a new topology. You can check this is a Grothendieck topology, and it has some funny properties, right? So for example, the spectrum of the complex numbers, of course, can be covered by the empty set, because right, the realification is empty, so the map will be surjective. So this kind of topology, it destroys everything which is not orderable. So it basically immediately puts you into characteristic 0, and it also, I mean, if you're algebraically closed, everything is already gone. It's basically about somehow, well, real points.
Try to say that again, like a little bit slower. So
yes.
What happens for the complex numbers?
Well, for example, the empty set goes to the specs C. This is the covering in this topology. So if you like in the category of sheaves, the representable sheaf specs C, in fact, it's isomorphic to the empty scheme and to the initial sheaf, right? Because you take the check nerve of this, but every term will be the empty set. Take the geometric realization to get the empty set. For example, so that's the sort of thing which happens. Also, anything in finite characteristic, again, will die.
Because it's not orderable.
Right, so nothing in finite characteristics is ever orderable. Yeah, so some of positive things should be positive, and -1 is basically always negative. So some things like that are axioms which I didn't write out.
So can I ask, the points which have an ordering, is there a topological property among for this subset? The X is in X, but there is at least one ordering on the residue field. Is that open, close, something?
I would guess it's. I'm not sure, but I think it can be. Okay. So that's the definition of the topology, and we could let's go on. But I want to point out something, which is that. So if you take a function,
so if the points are not, if it's not orderable, you just sort of.
So if the field is not orderable, then the spectrum of that field
is empty. Yeah, so you just throw them away somehow. Okay.
But I mean, you could have like a scheme over R, and it has some complex points and some real points. And so this guy in here, then it only sort of knows about the real points. So make a bunch of étale coverings which hit all the real points. They might miss some of the complex points, but it's still allowed as a covering.
Okay.
That's somehow how it works. Okay, so what I wanted to say is if you take some function on x, right? So then there's a risky topology of x. So how does that somehow arise? Is what you say, well, you look at, if you take a point of x, right, so you can evaluate f at that point and you get an element in the residue field. Now that's a function with sort of values in varying fields is a bit weird, but you can certainly ask if it is 0 or not. And you look at the set where it's not 0, that's you call it a sort of basic open set, and these kinds of sets, they described as a risky topology on x. That's just basically how you do it. Right? And now that we have ordered the residue fields, right, we can ask moreover if a function is positive or negative, for example. So we can look at this sort of set. So this set f, right, I know. So the set sort of x comma alpha in the realification, such that so f of x, right? So this is in k of x in the residue field, and it's ordered. So let's say it should be greater than in the sense of alpha, right? Should be greater than 0. This is the set which now makes sense. So this is the subset of Rx. And what one declares is that this sort of thing should be an open set. And then basically there's a topology on this Rx thing where the open sets are somehow unions or finite intersections of these kinds of guys. And so that's the topology which one is interested in, this real space. This here is the so-called, also is called the risky topology, I think. Okay. That preparation, I can state one very important theorem in this subject. And basically, as far as I understand, with the birth of the subject, this was sort of conjectured and proved. And so it's due to two people, one whose last name is Coste, I think, and the other one whose last name is maybe? Yes, but okay, I don't know if there's more to the story, which I don't know, but anyway. So they proved sort of the most basic version, and Scheiderer had some things to say about it.
It's a couple.
Sorry, what's that?
I believe it's a couple, no?
That was the implication which I wasn't super informed about. Right, okay, Scheiderer had something to say about it, and then there's an infinity categorical version, which is Mantou-Shah. But the statement is the following. The statement is that the real étale topos of a scheme, if you build it correctly, namely out of étale X schemes, this is spatial, which means it's equivalent to sheaves on a topological space, and I mean which topological space is going to be. Is it going to be? Of course, it's this one. So they prove the following thing, is that if I look at the category of étale X schemes, okay, so this is a category, and I can make it into a site in the sense of Grothendieck by using the real étale topology, of course. Then I get a notion of sheaves on it. So you look at this category of sheaves in the real étale topology, like this. And what you find is that it's the same thing as sheaves on the topology, as I said, it's the same thing as sheaves on this topological space. Okay, so this guy is a topological space. Okay, and so I'm thinking here of, so these people, of course, they proved it for sheaves of sets, and these people proved it for sheaves of spaces. This is sort of the hard part, and then there's some formal reasons why it follows for sheaves of spaces. Right, and let me make one further remark, which is that, so if the scheme X has locally finite Krull dimensions, of course, I mean, I write words like these, and in my head it's not completely insane. So in any case, if you take a scheme which is not completely mad, then, I mean, what's going to happen is that this Rx thing, you can check is, well, you can always check this is a locally spectral space, and because it has a locally finite Krull dimension, you check that this locally spectral space also has locally finite Krull dimension. And whenever you look at sheaves on a locally spectral space of locally finite Krull dimension, this thing has a locally finite homotopy dimension, which means that sheaves is the same thing as hypersheaves. Now, if these words don't mean much to you, forget about it, but for the experts, that means that we don't have to worry about certain subtleties which sometimes arise, but in the real étale topology, largely, it's not relevant. That's, okay, so I'm going to write this now, but so if X has locally finite Krull dimension, then Rx is locally spectral of finite Krull dimension, or is locally finite Krull dimension, and therefore sheaves on Rx has locally finite homotopy dimension, and therefore sheaves is the same as hypersheaf. Okay, so that's about as much as I want to recall or introduce about the real étale topology for now. Any questions? Good. Okay, so then I will try to now state my main result. So I need one more definition before I can start. And this is, I need to tell you what the category of Motivic real étale spaces is. So I denote this by FPC red of S, so S is a scheme. And so in principle is a very easy definition. It's just a subcategory of the category of pre-sheaves of spaces on something, and that something is the category of smooth S schemes. So if you know anything about Motivic homotopy theory, you know that this is always somehow the game that we play. We start with smooth S schemes and we universally adjoin colimits, and then we do some localizations, and you get some category which is impossible to understand. Then you're stuck.
Then you're done.
Okay, and so what is this sub? Right, so a subcategory means it has appropriate properties, then it is a localization, and it will be one of those, which is a localization. Just left that right here. And it's a subcategory, so consists of pre-sheaves which satisfy true properties, and I mean, I think you can guess what they are, right? So the first is that it should, of course, be real étale sheaves. Because why else would I put this? And the second is that they should be what's called A1 homotopy invariant, right? So it should be A1 invariant. I.e., if you take one of these sheaves in there, you take the value on some scheme X, you took the value on the scheme X times A1, there's a natural map between these two spaces, and that should be an equivalence. Okay, so we're looking at sheaves of spaces which happen to have these two properties. And the theorem is that we can understand exactly what they are. So the theorem is as follows. So we start with the real étale sheaves on Fs, okay? So this is this small category which we talked about, which is the same thing as the sheaves on the space Rs, okay? And so this is built out of étale schemes, this is built out of smooth schemes, so I can certainly, every étale scheme is smooth, so I can go from here to there, so there's a functor in this direction. It's a left adjoint functor, and it turns out that this is an equivalence of categories. So that's the theorem. And so this is, in some senses, quite surprising because maybe you know that if instead of the real étale topology you do the topology that we normally put, which is the Knebusch topology, then this is very far from true. Anything like this. So this category then is even more mysterious because I guess now it's not so mysterious because this I would pretend is sort of understandable. Yeah, so one could also call this somehow unstable real étale rigidity maybe. So rigidity is often considered in the étale category, and there you have a similar thing that somehow if you have transfers and you're A1 invariant and you're an étale sheaf, then you're also sort of locally constant, which is also surprising, but okay, it goes back to Suslin and Wojewodsky, I suppose. And it turns out that if you make the real étale thing, then it's also true, except you have very much fewer functions, right? There's no stability, there's no transfers, it just happens to be true on the nodes. So I think that's kind of cool. Any questions?
Can I ask, so this real étale sheaf, because the complex number is a Galois extension of R, is it somehow also like a C2 fixed point?
No, the complex numbers are like the empty set in this world, right? So the reals are this stock. There's nothing.
So I shouldn't think of this real étale sheaf as like, some C2 fixed point on a category or something like this.
No, I think sometimes you can put the real étale and the étale things together and then it behaves like sort of genuine C2, but it's sort of separated out here.
Thanks.
And will there be a separate real Knebusch story, or is it just the same as real étale?
I don't know, right? I mean, real Knebusch, as you know, of course, means that the residue field extensions should be the same, and real étale means that there should be a lift of the ordering. I don't really know. Of course, if they are the same, then there will be an ordering. So any Knebusch cover is also a real étale cover, but I don't know how else to put them together. Okay, so most of the words have been explained now, except maybe for revisited. So maybe I what is being revisited here? And so the point is that, I mean, maybe it would be more sort of in keeping with the theme of this workshop to do something about the stable homotopy theory, because then at least I can offer triangles. So we have spectra, right? So schemes have spectra in them, but there's no triangles, there's nothing stable going on. And, well, of course, once you have the unstable result, what do I do? Not like this, apparently. Okay, now we have it. Okay, right, so I can stabilize both sides. So I have some category of spaces, I stabilize it, I get spectra.
Are you sure you don't want to remove the water from?
I should probably, that sounds like a
German.
good plan.
Are you not German, actually?
I am German, actually, yes.
much time in Scandinavia.
Right, I was going to do spectra. So I can do really tall sheaves of spectra instead of sheaves of spaces, because why not? And I can do sort of the Motivic version of stabilization here, which means that one inverts the projective line here, normally. Then you get something called Motivic stable homotopy category. And of course, what you deduce is that this is also an equivalence. And my point is that this was proved some years ago in one of my first papers, maybe. So that's why it's revisited, because I proved this result stably some while ago, and now I can prove it also unstable, which I think is kind of cool. And I would also point out...
So try to say what the words mean again here, just so we...
This means just the stabilization of this category in the sense of category theory. Is you invert the action of the circle.
Okay.
And here you invert the action... I mean, you pass the pointed things first, right? And here you invert the action of the projective line, which is some version of S2, right? That's the definition. If you invert it here, then you get this. It's called Motivic spectra. So people have cooked this up and it seems to be interesting. Yes, the other remark which I wanted to make is that this is actually describable in another way, which is you take the usual Motivic stable homotopy category and you invert a certain map in it called rho. And I'm not going to tell you now what it is, but just if you happen to know this story. And then you could ask, can you also unstably, right, describe this localization somehow, real time localization as inverting the map rho, whatever that means. And the answer is that I have some results, but they're much more restrictive. So this is over any field whatsoever, and for any space, no assumptions, none. And I can prove something like this, maybe over a field if you have a simply connected space or something like that. But so I'm going to talk about that more general thing today. And in fact, I mean, the rest of my time I want to spend on trying to explain how to, well, give some ideas on how one proves this. And so the point is, well, one point is that, I mean, as I just said, I mean, it's super general, and there's not a whole lot being put in, so you cannot, there's not a whole lot of things you can do, right? So that's why there's a chance that I can explain this. So I don't have to explain what Motivic spectra, I don't have to do all of this nonsense. You get your hands into the only things that you have.
Can I ask just sort of, in terms of understanding, so is it clear that you can even like get the real étale from the stable one just by, why should you expect that you could get it from localizing something?
No, I don't know why you would expect, but I found this category first, and later I found it's equivalent to this, and it's equivalent to this, and this was like a circle of ideas, which I found quite fruitful for my work. And that's why I said revisit it, because there's some... No, it's not at all. I mean, if you make this obvious, please tell me. I don't really know why this works.
You're sort of, you're putting in this ordering thing, right? So.
Yeah, that's why. I don't, yeah. I mean, it's related to some theorem of Jeremy Jacobson, that if you take the Milner-Witt K theory somehow, and you take the co-limit in the rho direction, you get some real étale thing, but I'm not sure. Yeah, still mysterious to me.
So you said that all the result follows from this one. But
well, if you remove this part,
I mean, you could here also just stabilize with respect to the trivial sphere on both sides.
Yes, that's true.
Why is it that the right-hand side gives you, in particular, it gives you the same answer, right, on the right? So why is it that the P1 gets inverted automatically once you have it?
I don't have like a super rigorous argument right now, but roughly speaking, let's say S is the real numbers, and this is then this is just usual spaces, and this is Motivic real étale spaces. And what is this functor? Is basically take the real points, and P1 turns into S2, right? And if you invert S1, then of course you also invert S2. Right. Now, motivically, this argument doesn't fly, but somehow once you put in the real étale topology, the P1 becomes it. Or the DM turns into S1. Something like that. Or S0, I guess. Yeah, you have the real points of... Well, I have to... No, the real points of P1 is S1, right? So, not S2. So, GM turns into point. Sorry, yeah?
So you're saying somehow the real world, we should use it as being somehow simpler, because somehow there's not this distinction between the two different spheres. Was that one?
Yeah. It seems much simpler. That's exactly right. So this category also very hard, and then if you invert this one element, you get something which is much more understood. So it means if you happen to, by luck, live in this world, then you can answer questions, but it also means that you're not seeing very much of this complicated pattern. Okay, so now I want to prove this. So how am I going to do it? So I could write it the proof strategy for the theorem is that I'm going to want to prove two things, right? I'm going to prove 1 and 2. And so one is that I want, yeah, so what am I going to do? I'm going from real étale sheaves on this, and then you pull back to okay, so I look at the real étale sheaves of spaces on X, and I look at the real étale sheaves of spaces on A1 over X, and what I will want to prove is that this functor is fully faithful. And the second thing which I want to prove is that if I take X, which is smooth over S, then if I work in this, if I look at its image in this category, then it can be built out of étale schemes, right? So you know if you take a normal space, you can somehow build it out of points by gluing them together. And so what we're claiming here is to take any smooth scheme, you can build it out of étale scheme. So it's not, that's also very much not true in the normal Motivic world, where you absolutely cannot do this, and it's like the source of many complications. So this is also what I will want to prove. So can, in this SPC red category, be built out of étale S schemes. Now, if you can prove 1 and 2, I claim it is easy to prove the theorem. And so the basic point is as follows, right? So we have some functor, you want it to be an equivalence, so you prove that it's fully faithful and essentially surjective. And so this guy here means, right, that if I close the image of this category here under colimits, then I get everything. So I basically just have to prove that this functor from here to here is fully faithful. And now if instead of, right, so there's some A1 localization and some real étale localization, and if I didn't put an A1 localization, then it would be fully faithful for sort of trivial reasons. And so then the claim is, right, if you look at this, what it will say is that if you start with a real étale sheaf on the small side, and you extend it to the big side, then it becomes A1 invariant. This is somehow contained in here. And once you know this, right, it means that it's unaffected by this A1 localization, and so the fully faithfulness remains true. So if you prove 1 and 2, then by sort of standard arguments, you can quickly prove the theorem. So I will try to tell you how to prove 1 and 2. Yes, all right. Where are we erasing there? Now is the time for the Christmas song, is it?
Now I feel there's too much pressure. There's simply too much pressure. I can't do it. Oh, okay, little. Jingle bells, jingle bells.
Just when we thought the joke was
Thank you.
You're welcome.
Okay, so it can't all be formal nonsense, so we have to input something at some point. Okay, so I'm going to talk about what I call interval-shaped objects, or opens. Right, okay, so as I said, we need to input something, so now I have to tell you a little bit more about semi-algebraic geometry and this real étale topology and stuff. So the first concept, which will be relevant for us, is a so-called real closed field. So a field K, or an ordered field K, or no, a field K, is called real closed. if the set of squares forms sort of an ordering. So if okay, so you look at all the squares. Now, all the squares, of course, are non-negative in any field, in any ordering. But you just ask that, like, this should already be an ordering. So, for example, for any element, either the guy or minus the guy is a square. That would follow, right? So, if this guy is an ordering. And one can prove, for example, that if you take a real closed field, you adjoin a square root of -1, which this doesn't have because it has an ordering, then you get an algebraically closed field, that sort of thing. Okay, and then we have some facts. Let's see. So the first is that if you take an ordered field, then it has a real closure which is unique, in fact, up to unique isomorphism. It's a bit different from the algebraic closure, where it's unique up to non-unique isomorphism. It's sort of the whole point of Galois theory, I suppose. You can have automorphisms. But so if you have the ordering, then it turns out there will be no. So this means it's an algebraic extension of K to a real closed field, which is order preserving, and then any two such things there will be. So there's no automorphism of this preserving the order in any two. Okay, so if this is an ordered field, then it has a unique real closure. So one equals algebraic extension, which is real closed. And order preserving. Okay, so that's one fact, and then why do these real closed fields show up? The thing is, of course, we're doing sheaves, and so what you want to know about sheaves, the one thing which you probably want to know is what are the stalks, and the stalks in the real étale topology, they're the Henselian local rings with real closed residue fields. So you might remember in the étale topology, it's Henselian local rings with separately closed residue fields, and so real étale topology, real closed instead separately closed. That's some facts which people have figured out. So the Henselian local rings with real closed residue fields. This is the stalks. Okay, so that was one family of facts that I wanted to tell you about, and here is here's a different family of facts. And it goes like this. So suppose that K is a real closed field. Then, so what you can think about is what are the points of the realification of the affine line over K? Well, I mean, you can start with, of course, the spectrum of K, but it will have a unique ordering, and so the realification of that is just one point, so it's very boring. But you can figure out this thing, so the points of okay, so this can be determined explicitly. It's not that easy, to be honest, but of course one can find it in books. So they are as follows. And I guess it's going to be quite illustrative to sort of how this real spaces thing behaves. So there's one very obvious family of points, right? So any number in K. So if X is in K, then I mean the affine space over K has a closed point corresponding to this number, and the residue field is K, and it has its unique ordering. So there's going to be an obvious point in the realification. So for X in K, a point X with residue field K and unique ordering. Okay, so there are other closed points, of course, but then it will be the sort of the complex numbers of this world, and so they don't count, they don't have orderings. So all other points, they come from the generic point. So there's a unique generic point, which is the function field of the residue field is the function field of K. and you can ask just what are the orderings of this, and it turns out that one can figure this out. Okay, so there are many orderings of a function field in general, but so there are two which are called plus minus infinity. So these have residue fields. K of x. And so the ordering is basically that you look at the sign as you go either to plus infinity or minus infinity, right? So these are rational functions, have finitely many poles, so you can somehow, if you imagine making your x very big in the sense of the ordering, it will not have poles anymore, and it will have sort of by some not really continuity, right? Because it could be the reals then by continuity, and in general, just by some algebraic analog of continuity, it turns out that it will just change the sign only finitely many times. So there's like a well-defined sign at infinity, and that's how you the out of a function should count as positive or negative. Okay, with residue field k of x and ordering by sort of the sign plus minus infinity. But that's not everything. So for the reason, so if k is r, then this is the only options. But if k is not r, even more. So what you can do is if you take something called a proper Dedekind cut. So I'm not going to explain exactly what a proper Dedekind cut is, but what you imagine is you take this field, right, it has an ordering, but it's not complete as a topological space. So you can make it complete, and it turns out that there are several ways of making it complete in general, and Dedekind cuts is somehow the right way, but basically it's like you have some holes in the space, and you can arbitrarily come up with them. And so proper means that it's not actually already in your space, right? So you're looking at an actual hole in some sense. Then there will be 2 points. X bar plus minus is how they're usually denoted, and basically they will give you, right, if you take any polynomial function or rational function, let's say, you can evaluate it on this on this completion by continuity again, and so you can ask about the sign just to the left or to the right of it. And notice that it can't be 0 or infinity at this value, because well, that seems to be a fact. Sorry. Okay, there are these 2 points, with residue field k of x and ordering by the sign so just left or just right of x bar. And so this is quite funny, right? I mean, you stick in this easy definition, and this is the space that comes out. I would point out that this is a compact Hausdorff space. It's basically, right, just sort of, well, I've given you all of the points. Wait, is it Hausdorff? Maybe these 2 points are not. So maybe you have to look, you have to collapse these things. But it's certainly compact. It has very good properties. That's somehow one of the themes in that you build these spaces with these somewhat strange orderings or extra points put in, and then things behave much better than you usually expect in algebraic geometry somehow. But,
so when you plug in k equals r, then you're saying that it's compact because it's just a closed interval or something like this?
If k equals r, the third kind of points do not arise, and you literally get like the real numbers with plus minus infinity, which is of course homeomorphic to the closed interval. Yeah? But this is the only field where you don't have the extra points in the last type. Okay.
So what are other real closed fields that we should think of?
Well, I guess you can take you take the real algebraic numbers, so take algebraic numbers intersected with the reals. But I'm not sure how. I feel like this is sort of a bit misleading, because you can take you take something like the real closure of this kind of function field in one of these order rings, and I think this will give you another, well, it will of course give you another real closed field, but they're sort of, I think, quite different from the two that we described so far. It's a good question. I'm not sure how to think about this. Okay, so the key lemma.
You might want to again remove the order.
Thank you.
You're too quick. I was almost getting a song ready. But
Okay, I think I'm going to erase enough that you can sing another time. The key lemma is the following. My key lemma is the following. So let X be a scheme. F a function on X. And so I'm going to view this as a map from X to A1 over X. Okay, so I have A1 over X. And I have X, so there's a map here, always the projection, and this F provides me with a section. Okay? And so now I assume that I have some open subset in the realification of A1 over X. And what I want is that it should be an open neighborhood of the image of F. Okay, so I guess contains realification of X. Okay, and so then I consider the following subset. I said U prime. So this will be a subset of the realification of A1 over X, and it's the following. It's the set of all those points in U such that the interval, right, between U, which is some guy here, right, I can go down, I can go up again, I get some other point in the same fiber. So that fiber, of course, is A1 over some real closed field, so we know what this looks like, so an interval makes sense. And so what I'm going to want is that the entire interval should be itself contained in U. So this is all those U such that the interval from U to F of P of U should be contained in U. And the claim is that this set is open. Okay, so I'm not going to prove this. So you need to, I don't know, once you have this idea, I think if you find yourself a book about semi-algebraic geometry, you will find a way to prove this, probably. I just wanted to give you a picture, okay? So what's going on? What's going on? Maybe I'm giving myself a bit more space to draw.
I'm dreaming. Just like the ones we used to know. I'm dreaming of a white Christmas. I don't know the other words.
Okay, so here's my X. And here's A1 over X. And then my F, this is some kind of section, so I don't know, it looks something like this maybe. And then I have the U, which is some open subset which contains this. So I don't know, maybe it's, I don't know how to draw this, yeah, something like this maybe, something like this. Oh no, something like this, right? And now you take any point, let's say here, and you ask, is the interval from this point, is it contained in U? And it is, right? So then you're allowed, you put this in U prime. Whereas if you take, I don't know, this point here, you make the interval and then you're not, you're missing it, okay? So now what we are going to do is, so this is U, and then U prime is going to be something like, well, it shouldn't go over first. Something like this. Okay, and the claim is that this is still open. And I mean, if you look at the picture, this seems pretty convincing. Of course, there's not a proof.
It looks asymmetric. I mean, you mean U, FPU, or FPUU or something?
Yeah, whatever. That's right. You have to do it in the right way. So that I'm not sure. Or I mean, it's exactly what you said. Either this or the other one, whatever makes sense. So one proves that this is still open. And of course, I mean, it's not a big surprise why I want this, because once you have this kind of set, you can contract it, because there's like a choice of base where I can contract it too. Okay, and so now the definition is that I call such an open subset U prime interval shaped. Of course, the U prime, it also depends on the choice of F and X and so on, but let's not be overly pedantic. Okay, so then I was, one corollary, which is that any open sub, right? So now I'm not assuming, yeah, so let X be arbitrary or something like that. And then the point is that any open subset of the realification of A1 over X, it can be covered by interval shaped things. So it's possible that in order to make it interval shaped, you have to make X smaller, right? So you find some open subset of the real space of X, and then there's a section over that open, and then you can make something around it. But that's what I want to allow this sort of in the loose language that I'm using here. So let X be a scheme. Any open of the realification of A1 over X can be covered by interval shaped. Shaped opens. Okay. So now I only had 2 pages of notes, and I thought this was going to be too little, and turns out I was wrong. So I think I'm going to skip the proof of 1. Also use the key lemma, but I think it's less fun than 2.
Rocking around the Christmas tree, have a happy holiday. Okay, I think now we should move on to something different. Unless you want Last Christmas, you know. So
Maybe a Danish Christmas song. Is real closed equivalent to being index 2 in its algebraic closure?
Yes.
Good.
Yes, I think I remember that is a theorem. It's not obvious to me. So I'm not proving 1, I said? Yes, I'm proving 2.
Could you restate 2?
Right, I'm going to give it to you at the end, but the statement is that if you take a smooth scheme over S, you can somehow build it out of étale S schemes in the real étale topology with somehow affine homotopies, affine line homotopies. So the definition is that if you take some function or some scheme is called totally positive, if, I think you can guess it, right? If for any point in any ordering, the value is positive. So, I guess. Many ways of saying is that for every spec R to X, where this guy here is really closed, so that f of R, f of R, I guess this would be alpha, yeah, alpha f should be bigger than 0. And one has the following lemma, which is that if you take a real Henselian local ring with real closed residue field, then any totally positive element of A has a unique totally positive square root. Okay, I mean, this is fairly straightforward. In the residue field, it's positive, so it has a square root, and then you can always lift because of the Henselian property, and then you need a little bit of argument for the uniqueness, and that you can choose it to be totally positive and so on, but it's fairly elementary. And so why do I care about this? So the corollary is that if you look at the structure sheaf, OX, and I take the associated sheaf in the real étale topology. So one fact about the real étale topology is that it is not subcanonical. So in the étale topology, you take the associated sheaf, it doesn't do anything. But in the real étale topology, it does. So in this guy, what we are going to in particular conclude is that totally positive elements have square roots. And so what this tells you is that in the world of semi-algebraic topology, right, in algebraic geometry, you can only use polynomials, maybe rational functions. In semi-algebraic geometry, you can use square roots. So you can cook up a lot of functions if you're allowed to use square roots. And so that is, I think it's going to fit. So I can show you an interesting function. So consider the following function. This will be f, and it will live in. It will be a function on the affine line. It doesn't really matter what the base is, z or s or q. It will be a universal thing that I can do. And it will be the following function. So it looks a bit weird, but it's 1/4. Okay, that's the function. So there's a 1/4 here, which maybe you're concerned about, because what if I'm doing this sort of with the integers where you can't divide? But notice that, of course, I mean, any real closed Henselian evaluation ring with a real closed residue field is characteristic 0, you can divide, right? I mean, this is a characteristic 0 problem. So apart from that, okay, so I take something which is totally positive and I add on a square, so this is totally positive. So I'm allowed to take this square root, and then I subtract off some things and some squaring and some quarter, I mean, whatever. I am allowed to do this. So now why? Why do I want to look at this function? Obviously you can find many other functions and they will do the same thing. But let me sketch it for you. Or I mean, you put it into Wolfram alpha and then believe that this is the sketch. But so here's the sketch of the relevant properties. So what's going to happen? What's going to happen is that at 0 you get 1, right? So this is 9. So it's 3 minus 1 is 2, squared is 4, divided by 4, at 0 you get 1. Okay, so that's a relevant point. And at 1 you will get 0, because I've cooked it up in that way. So this is 1 here, this is 1, and at minus 1 you also get 0, because it's symmetric. And so if you let it go to infinity, then you get a quarter. So it will eventually somehow have some asymptote here. And it turns out it looks like this. Something like this. Okay, so the point is that it's, at 0 it's 1, at 1 it's 0, and it always stays between 0 and 1. And what this means is that I can use this function to write down a homotopy, to use the affine line to contract the closed interval from 0 to 1. That's the main point. And so this I can use to finish off the proof of 2. Okay, so this will go as follows, so that...
I'm confused why you get a quarter at infinity.
At infinity, well, maybe I did it wrong, but doesn't this turn into 4? Should it be to the 4th here? Is that what we're concerned about?
No, so if x is infinity, that gives you infinity. I think you need to divide by something if you want an asymptote.
No. I mean, if x is very big, then this is basically 16x to the 4th, and so if I...
16 times a large number is also a
No,
large
but like
Yeah, but then you're subtracting
warm that
4
point.
as
Subtracting-
well.
Okay, I'm sorry, I'm being stupid.
I mean, maybe this should, I think this should be 4, right?
Yes.
Yeah.
I think I have an actual proof, which is not put it into Wolfram alpha, but... Okay, so now I will finish it off. take U contained in A1 over X, and I assume that it's interval shaped. Okay, so what this means is that, so I have some V from, so V is contained in the reedification of X, and then with the map here, the reedification of A1 over X, and in fact factors through this U guy, like this, right? And then somehow the interval is always contained in every fiber. And then I define H. What do? Yeah, U cross A1 goes to U via H of X comma T equals, so this is my function, no, this is not F. I have to call this G now, because this function over there is F. Okay, sorry about that. So it will be F of T times X plus 1 minus F of T times G of X. Okay, so the point is just, I mean, it's the same picture that I had before. This is what U looks like, and there's some. And what happens is that every point gets contracted to the point in the fiber where my section goes. So this is a linear homotopy between, of course, well, this point and this point. And because of the way that this F is cooked up, this really moves from here to here and nothing else, right? So it moves a little bit in both directions, but it never moves outside. So you don't do this sort of thing, which normally if you write down a homotopy using polynomials, it will sort of outside of the values between 0 and 1. It does something crazy, but because we have this funny square root functions, I can do this. And that should be the end. And so, yes, I think I'm basically out of time, but so from this you can make it work, right? So the point is, this shows that U to V via, I guess, P, and this map back via G, these are inverse A1 homotopy equivalents. Okay, and so what this means is, what I've proved is that interval-shaped opens in the affine line over X, they can be built out of étale things sort of over X, right? So this comes from this V guy here. So now how do I conclude? Well, if I take a general thing inside A1 over X, then I can cover it by interval-shaped things, and then I intersect them, and actually they're still interval-shaped, but you could refine. So you can build every, right, because every open can be covered by interval-shaped things, it can be glued from interval-shaped things. So if you want to get any open here in whatsoever, you can still build it out of these kinds of guys. And so of course, in general, I'm not supposed to be inside A1 over X, I'm supposed to be in some smooth scheme, so I know why. But this, at least locally on Y, it's étale over an affine space, right? So it goes to AN over S, which I can project to A n minus 1 over S, and you see, this is an A1 over its space, so this tells me that this guy I can build from étale things here, so this some Y prime goes to here, but then I can, of course, keep going, right? So A n minus 2 over S, that's the Y double prime here, and so if you work down this power, this will eventually prove what I wanted, that every smooth scheme, it can be built using, well, A1 homotopies and the real étale topology from basically just étale-less schemes. And that's all I have time to say.